Math, it's all about math, the wonderful world of math. Welcome to the wonderful world of math. Today we want to talk about the binomial theorem and revisit some binomial coefficients. What are binomial coefficients? Well, binomial coefficients are what we're talking about when we say, hey, you know this binomial, what happens if I raise it to lots of powers? What happens if I say, raise it to the third power? Well, you're going to get a bigger polynomial, a polynomial with more terms. It won't be a binomial anymore, it'll be a power of a binomial. And you're going to get stuff like this. Powers of a and b, and all the various ways you can do that that have total degree for each term 3. And I realize that this is a 3. But based on the binomial power, you're going to have different coefficients for each term. We talked about how you could do this last time with Pascal's triangle. This one was going to be 1, and 3, and 3, and 1. Pascal's triangle was a cool way that we could figure out the binomial coefficients of the next biggest power of x by putting a 1 and a 1 on the outside, and then having all the stuff in the middle just be the sum of the two diagonally above it. So 1 plus 3 is 4, and here 3 plus 3 is 6, and 3 plus 1 is 4. And this was Pascal's triangle. And Pascal's triangle works great if you want to use relatively small powers of a plus b. So like a plus b parentheses to the 4th or 5th or 6th or even 7th or 8th. But if I want to do a plus b parentheses to the 20th power, I don't want to have to go through the triangle and figure out all 20 rows before that, which is what you would need to do. So we're going to use the binomial theorem, which will allow us to do the 20th one without having to figure out all the stuff that came before it. If you're familiar with sequences and terminology from sequences, the Pascal's triangle is like a recursive sequence, a recursively defined sequence, where you use the previous row to get the next row. The binomial theorem will allow us to do this by finding a formula for the nth term. A non-recursive way to say it. So here's the binomial theorem. Right now it involves some notation we're not familiar with. We're going to go over this in a second. But it's telling us, what we can understand so far, is that we've got some coefficient, with some weird notation for now, times the power of a times the power of b. And now in this first term, the power of b is 0. You'll notice that the total degree of this term, n plus 0, is n. Here, the total degree of this term, n minus 1 powers of a, 1 power of b, n minus 1 plus 1, total degree, n. Every one of these terms is going to have total degree n. Each time we have one less power of a and one bigger power of b, starting the a's at the nth power, the maximum power, and going down to 0 powers of a, and b's doing exactly the opposite, starting with 0 powers of b and getting one bigger each time to get the maximum n powers of b. So what are these coefficients? This notation says the binomial coefficient for the kth term of a plus b parentheses to the n is given by this equation. N factorial over n minus k parentheses factorial times k factorial. If you're familiar with it, this is exactly the same formula as the combinatorics formula n choose k, the number of combinations when choosing k objects out of n total objects. So if I want to say pick 2 people for our astronomy club's snack committee, and there are 15 people in our astronomy club altogether, the snack committee of 2 people will be the k, and the astronomy club with 15 total people will be the n. Right? Combinations choosing n objects out of k total things, where the order is not important, repetition is not allowed. I can't pick the same person twice to be our snack committee. I need 2 different people. And that all of the people in our astronomy club are different from each other. This binomial coefficient and this number of combinations have the same exact formula. So if you know this, this should be pretty familiar. If you don't, you're probably wondering what this exclamation's doing here. So, hold on. Factorial. This exclamation mark is called factorial. N factorial means for all natural numbers, that is n starting at 1, 2, 3, 4, etc. N factorial means n times every natural number smaller than it. So n times the next smallest natural number, n minus 1 times the next smaller one after that, times dot dot dot, until you get to 4 times 3 times 2 times 1. And of course the times 1 doesn't do anything, but it helps preserve the pattern, so we use it when we're getting used to it. For example, if I say 5 factorial, this is 5 times every natural number smaller than it. So what's the next smaller number than 5? 4. What's smaller than that? And 3, and 2, and 1. 5 times every natural number smaller than it. And this is going to be 120 once you get down to it. What is 4 factorial? Well, 4 factorial is 4 times each natural number smaller than it. It ends up being 24. One of the things that you might want to notice is that 4 times 3 times 2 times 1, that's 4 factorial, right? So when you see 4 times 3 times 2 times 1, you should be able to think, hey, that's 4 factorial. For example, up here, 5 factorial is 5 times, wait for it, 4 times 3 times 2 times 1. What is 4 times 3 times 2 times 1? This stuff is 4 factorial. So I could also write 5 factorial as 5 times 4 factorial. Sometimes it is helpful to be able to do this, especially if you're going in order. Last step, to do 4 factorial, I said that this was 24. To do 5 factorial, I take the old answer, 24, and multiply by only one new number. Pretty handy, right? For example, let's say I want to do 6 factorial. I know that that is 6 times 5 times 4 times 3 times 2 times 1. Well, we actually know all of this stuff. This stuff is 5 factorial. I could write 6 factorial as 6 times 5 factorial. And we know that's 6 times 120. But I could also write 6 factorial as 6 times 5 times 4 times 3 times 2 times 1. And we know that this is, wait for it, 4 factorial. So if I know these things, I can say 6 times 5, that's 30, and 4 factorial is 24. And this is going to be 720 also. So in addition to those, we've got some other things. We wanted to say 3 factorial. That's 3 times 2 times 1. 2 factorial. That's just 2 times 1. 1 factorial is just 1. And that is as far as the standard definition of factorial goes. But we're going to need this next one also. And this doesn't fit the formula in the same way. So we say by convention. That means we all got together and agreed upon it. By convention, we say that 0 factorial is 1 also. We will need to use that. So let's suppose we're asked for this. The binomial coefficient for the third term in the expansion of a plus b to the 8th power. Also known as 8 choose 3, because the formulas are the same. So we're going to get n, that's the top number, factorial, over n minus k, parentheses factorial, times k factorial. That was our formula. You can go back and check if you want, but I'm pretty sure that's it. And then we start simplifying. 8 minus 3 is 5. Of course, 3 factorial is 3 factorial, and 8 factorial is 8 factorial. The first thing we should do is simplify 8 minus 3. You can do that in your head eventually when you get used to it, but for the first time I wanted to write it out. Now, 8 factorial is not that bad, but when we start getting up to something like 100 choose 48, you're not going to want to ask your calculator for 100 factorial and then divide by 48 factorial times 52 factorial. Your calculator will revolt. Try it. If you can't find the button, look for one that says X exclamation or N exclamation. Your calculator should have a button that says one of those. It will not like 100 factorial. So we're going to practice right now how to handle that. What does factorial mean? It means 8 times every natural number smaller than it. Oops, skipped one. We got to make sure we catch them all, like Pokemon, right? Okay, so that's 8 factorial. A product of 8 factors. We've got 5 factorial, 5 times 4 times 3 times 2 times 1, and we've got 3 factorial. Hopefully, you remembered to recognize stuff. 5 times 4 times 3 times 2 times 1, and 5 times 4 times 3 times 2 times 1. In the future, all we really want to do is figure out when I can start canceling easily. I know that 8 times every natural number smaller than it is going to have some of the repeat factors as 5 times every natural number smaller than it. So instead of writing out all 8 factors, I'm going to say, since I know I have a 5 factorial on the bottom, I'm going to stop writing this all out when I get to 5 and everything smaller than 5, so that when I do this the next time, I can skip this step. I'm going to go straight from here to here to here, because I know that this 5 factorial on the top and this 5 factorial on the bottom will cancel 5 factors at a time, saving some of my time. Not this time, but next time. And how many more times can I say the word time? Time, 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 time. Now what's left to cancel? We've got 8 times 7 times 6, and in the bottom we've got 3 times 2, and I'm going to stop writing the 1. So you just start looking. The cool thing about this formula, and that means these notations, is that even though it looks like a fraction, it will always be a natural number after reducing. That means that this 3 will always find a home up here, a partner factor to reduce. This 2 will also find a partner factor to reduce. Now you could put the 2 into the 8 and say there's a 4 left over, and you can put the 3 into the 6 and say there's a 2 left over. You could do that. I like to do it a different way. I like to say that, I actually know what 3 times 2 is. It's 6, and just get rid of that in one go, so that this says 8 times 7. 8 choose 3 is 56. For the next example, let's suppose n is 4, and we're going to find all of the n choose k's that we can. So one of the things about this formula that we hadn't said yet, and this is kind of important, we just had a lot of stuff going on, is that k has to be a natural number, or at least a whole number, that is less than or equal to n. So k and n, both natural numbers. K can be anything from 0 to n as long as it is a natural number. So when we say all of the possible n choose k's if n is equal to 4, that means that this is going to be 4 each time, and that k can start at 0 and end at 4, and it will take on every natural number in between. These are all the possible n choose k when n is 4. Great. We're going to do the first one together, and maybe the second one or the third one, we'll find out. Okay, 4 choose 0. The other way to write this as the combinations formula is going to be 4 factorial over 4 minus 0, parentheses factorial, times 0 factorial. Hey, see, I told you we were going to use that 0 factorial. Now, what's 4 minus 0? Well, that's 4. So 4 factorial over 4 factorial times 0 factorial. You should see one thing pretty clearly, that you got 4 factors in the top, 4 times 3 times 2 times 1, and 4 factors in the bottom that all match. Then the next thing, after canceling the 4 factors in the top, what's left in the top? Well, when I take all the factors away, the only thing left is 1. And of course there's a 1 left in the place of these guys, if you like. More importantly, what's 0 factorial? Also 1. Interesting. 4 choose 0 is 1 when you're done simplifying. 4 choose 1. 4 factorial over 4 minus 1 parentheses factorial, 1 factorial. Now this is 4 factorial over 3 factorial, 1 factorial. 4 factorial means 4 times 3 times 2 times 1. And you know that 3 factorial also means 3 times 2 times 1. So I actually don't have to write out all of that stuff. Let's observe that that is 3 factorial. And so this 3 factorial and this 3 factorial go away. What's 1 factorial? Also 1. 4 over 1, 4. 4 choose 0, 4 choose 1. So I want you to try these 3. Go ahead, pause this, work them out, and I'll wait right here. I'm just kidding. I'm going to go get a drink. Not that kind of drink. I'm getting a water. Probably. Just kidding. It really is water. Whew, that was a nice break. Okay, are you ready? Did you get these things? 4 choose 2. That means 4 factorial over 4 minus 2 parentheses factorial times 2 factorial. But 4 minus 2 is just 2. So this is 4 factorial over 2 factorial and 2 factorial. 4 factorial means 4 times 3 times 2 times, well, 2 times 1 is 2 factorial. It's not very exciting, but you can cancel this stuff. 2 factorial with 2 factorial. And 2 factorial, 2 times 1 is just 2. So you reduce and you get 2 times 3, which is 6. For the next one, 4 times 3 times 2 times 1 in the top, and 4 minus 3 parentheses factorial is really just 1 factorial. So when we say 4 factorial, the most convenient thing for us is to say 4 times 3 and everything smaller than 3 over 3 factorial, and the 3 factorials will cancel nicely. 3 factorial, but 4 is all that's left. 4 choose 4. 4 minus 4 is 0. 0 factorial is 1. Everything else was just 4 factorial. Cool, right? And that all goes away. 1, 4, 6, 4, 1. If you recall this much of Pascal's triangle, the coefficients in the fourth row for the expansion of a plus b to the fourth power is 1, 4, 6, 4, and 1. The same things that we're going to get using these. So the thing about those binomial coefficients is that they are exactly the same things that you're going to get from Pascal's triangle. Watch, watch. See? We go back and forth. Each of these numbers is equal to the corresponding binomial coefficient using the formula. As we saw with this row, 1, 4, 6, 4, and 1, we calculated these the long way, and we got the same thing as we did using Pascal's triangle, to just say 1's on the outside, and then the sum of the top two diagonal adjacent entries. So this is giving us the same information as Pascal's triangle, but will allow us to do it without having to do every row of the triangle between the one we started with and the one we need. I recommend you check the formula for all of these numbers, all 10 of those guys. Before we do another example, I'd like to talk about some properties of this formula, this notation. N choose k. First property, n choose 0 is always 1. N choose n is always 1. As an example, we've seen that right here, right? This. 4 choose 0 was equal to 1. This just says that that isn't special or unique. That's going to happen every time you have k equals 0. And every time you have k equals n. Just like when we had 4 choose 4, it was also 1. This is the kind of thing that you can actually prove from the formula. Let k equal 0. Let k equal n. Show that they're the same and that they're both 1. This is something you should be able to try to prove. The second property, n choose 1 is equal to n. N choose n minus 1 is also less than n. Well, let's think about this in terms of the combinatorics, right? In this one, we've got n things, and we're going to choose 0 of them. I've got 14 people in a classroom, and I'm going to choose none of them. How many ways can I do that? 1. There's only one way to choose no one. I've got 14 people in a classroom, and I want to choose 14 of them. They all get picked. There's only one way to do it. That kind of makes sense, right? But again, you can prove it using this formula. Here, I've got 14 people in a classroom, and I want to pick one of them to bring cookies next Wednesday. If there are 14 people in the class, there's 14 different people I could pick to be that one person. I could pick one person out of 14 different ways. This is a little bit like saying I've got 14 people and I'm going to leave one person out. I'm going to pick 13 people. One person gets left out. So I'm going to pick one person to get left out. The way to pick one person, to select one person, is really kind of the same as picking one person to get left out. There's 14 people to choose from. Any one of those 14 could be the single person who gets left out. So that's the 14 ways to choose who gets left out, and this is 14 ways to choose who does get picked. Either way, n choose 1 and n choose n minus 1 are both n. This is another thing that you should be able to prove with a formula. It should be pretty easy. N choose k is the same as n choose n minus k. For example, we did 8 choose 3 earlier. What this rule says is that if we do 8 choose 8 minus 3, which is 8 choose 5, you're going to get the same results. So 8 factorial over 8 minus 5 factorial times 5 factorial. But what is 8 minus 5? That's 3. So 5 and 3 and 3 and 5, the difference is just the difference of order. You end up with all the same factors, and so these are of course going to reduce the same way. They're just written in a different order. Here we have 4 choose 1. What's 4 minus 1? N minus k. N minus k is 3. 4 choose 3 and 4 choose 1 have the same value. What these properties are saying here is that all of the stuff on the outside, where we've got choose 0, the 0th coefficient, and all the stuff on the other outside, where the bottom number k equals n, k equals 0, k equals n, they're all 1 in this Pascal's triangle. The second rule says that this next diagonal, they're all going to be the same as this exponent, 2, 3, 4, 5, and that these guys are going to be the same thing. The third rule just basically says that this is symmetric, that if I cut this down the middle, this side is going to mirror this side. These things allow us to cut our work in more than half. The third one cuts it in half, and then the first two rules make these guys easier. This one should be the easiest of all to prove. So try it. What we're going to do is we're going to do one more example. So for our last example, for now, I want us to expand x plus yz parentheses to the 8th power. So let's expand it. Bump, bump, bump. It's expanded. Just kidding. According to the binomial theorem, which admittedly we haven't seen in a while, we're going to have these coefficients times powers of the first term and the second term. So this expansion here is going to have the first term, x raised to the 8th power, and no powers of the second term, yz. We will have a coefficient determined by the binomial coefficients, 8 choose 0. The second term is going to be binomial coefficient 8 choose 1. The first term raised to 1 less power, and the second term raised to the 1 more power. 1 more than nothing is just 1. The third term, or better yet, let's call this the 0th term, the first term, the second term. It's weird to start calling things the 0th term, but it makes more sense to call it the 0th term so that the number term you're on corresponds with k. So 1 less power of x here, 1 more power of yz. Well, yz is a product, so when I want to take 1 more power of the product, I have to use parentheses. Big deal. We've covered most of the important things, and we should be able to zoom right along now. 1 less power of x, 1 more power of yz. And let's cut to the end here. We've got, look at this, 9 terms. These 8, k equals 1 through 8, easy to count, plus the 0th term, 9 terms. Using our properties of this binomial coefficient notation, we know that 8 choose 0 and 8 choose 8 are both going to be 1. We also know that 8 choose 1 and 8 choose 8 minus 1, aka 8 choose 7, will be n being 8. That's 4 out of 9 of them right away. We also know that since this one and this one were the same, and this one and this one were the same, this one and this one will be the same, and this one and this one will be the same. We've got 1, 2, 3 more to find. That's it. With properties 1 and 2 and the symmetry of the third one, we only have 3 more to find. So see if you can find these other 2. Once again, I'm going to ask you to pause this and try to do this on your own, because it's better for you. Sort of like eating kale. Okay, I'll wait here. Psst, sorry to the kale lovers out there. Alrighty, are you ready? Have you calculated your calculations? 3, 2, 1, boom. 28. 8 choose 3 is the next one. You remember that guy? We actually did it already. 56. 8 choose 4. 8 factorial over 4 factorial, 4 factorial. 8 factorial becomes 8 times 7 times 6 times 5 times 4 factorial, right? And in the bottom, 4 factorial is 4 times 3 times 2. You don't need to say times 1. We know the 1 doesn't do anything at this point. But 4 factorial in the top cancels with one of the 4 factorials in the bottom. A 4 goes into the 8, leaving you with a 2. And the 2 and the 3 together go into the 6. Goodbye, 6. And the 5 is left, the 7 is left. 2 times 5 times 7, 70. You should probably check that 8 choose 5 is 56. Well, we kind of did that one already too. And that 8 choose 6 is 28. But they will be. The last thing we'll want to do is, before we move on to plugging each of these things in, 28 for 8 choose 2, etc., is reminding us that yz parentheses squared means y squared z squared, squaring everybody in that product. This is our final answer here. We've plugged in each of the coefficients where they belong. This is our 9-term polynomial. Before we go, we don't have time for another full example, but we do have time to state another important property of this notation. And this is really the important part of Pascal's triangle in terms of this new notation. For any non-negative integers r and k, and that just means like whole numbers, k choose r minus 1 plus k choose r is equal to k plus 1 choose r. For example, and oh, of course I forgot to say r has to be less than k. Anytime you put somebody on the bottom, it's got to be smaller than the one on the top, or at best the same size. So Pascal's triangle said that I take this one and add them together to get this one, right? What is this in terms of binomial coefficients? Well, it's the 5th row, 0th term, 1st term, 5 choose 0, 5 choose 1, 5 choose 1, 5 choose 2. Where here k is 5 and r is 2, so that this is r minus 1. 6 then would be k plus 1, and 2 is still r. Note that this is this plus this equals this. That was the defining moment of Pascal's triangle. That's what this property is saying. And that's all of our time for today. Our constellation of the day is Canis Minor, the little dog. Bark, bark, bark. And this has been a Badger Bear production of the wonderful world of math. Thanks for watching.